Hey, what's up? If you've installed an OpenShift 4 cluster or looked at installing a modern Kubernetes native application, then chances are you've come across the term operator. In this video, I'm going to cover exactly what an operator is. I'm going to look at why the Kubernetes world is embracing operators, and then I'm also going to provide some more context around the tooling surrounding operators, because in my opinion, this is where the lines can start to get a little bit blurry and make operators kind of seem a little bit more complex than they really should be. So let's start with a definition of operators from the OpenShift docs site. Operators are pieces of software that ease the operational complexity of running another piece of software. Okay, so we can say that an operator is basically a codified human being, a codified applications administrator, someone who would usually monitor the current state of an application that they manage and make decisions on operational tasks like backups, upgrades, error recovery, and all those sorts of things. So imagine wanting to run some Kubernetes native app on your cluster. Let's use a to-do list app as an example. Now this is a completely fictional app, so don't read too much into each component, it's just for an example. This app, in true Kubernetes fashion, is made up of microservices. It has a web server front end that serves the application so that you can add your to-dos, and a backend API connected to a database for persisting them. There's also a bunch of other Kubernetes resources connected into various components like an ingress config, services, a config map, and a secret. I could have added even more like service accounts, roles, role bindings, and all that sort of stuff. Now imagine you call up the software vendor that provides the to-do list app, and they send out one of their engineers to get things set up for you on your cluster. They come out, have a quick chat to you about your requirements so that the app can be configured appropriately, and then they install all of these components. They might use Helm, they might use a script, an app that they built, or even just manually provision things. It doesn't really matter to you because they're looking after it and they take ownership of the app. And once setup is done, that engineer just sits in your ops room and doesn't budge from maintaining your to-do lists. They keep your app running, apply updates as they become available, scale as needed, recover from errors, and create new lists when required. These are all very much the kinds of tasks an operator can do for you. So obviously, instead of sending out a person, the software vendor can instead give you one or more pods to run in your cluster, and those pods can have the domain-specific smarts built into them to perform all the same functions as that human would. Now, you might say, why can't they just give you the Helm chart or the manifests and you'll do it all yourself? And the answer to that is mostly to do with day 2 operational tasks. What happens if you wanted to upgrade the version of the app? Is there a specific order to do that in? Do I need to take a backup of the app first? If so, how do I do that? Is there anything new that has to be set in the config maps or the secrets for the new version? Do I need to manually choose a leader for distributed applications? What if there's another backend microservice that's introduced as part of an upgrade? What's the right way or order to deploy that? These are all questions that experts with the operational knowledge of the app can build answers to directly into the operator so that you never really have to worry about asking them. Okay, so in regards to the operator, for now, let's just think of it as a pod with software running in it that has the operational knowledge to administer the to-do list app on your cluster. There's another important piece that goes hand in hand with the operator though, something called the custom resource definition. Let's look at that. So keeping with the analogy, once the engineer is sitting in your ops room and has access to the cluster, it's easy enough to walk in and request a new to-do list instance be created by them. To collect the required configs, the engineer might ask you to fill out a form or something. That form might include fields like the name of the new list, the maximum number of to-dos the list should be able to hold, and maybe even what sort of level of availability that you need for your list. There might even be some details you don't know the answer to, but that would be okay, because if you left it blank, the engineer, with their in-depth knowledge of the inner workings of the app, could just enter some sensible defaults for you to get you started. So again, hopefully you're keeping up with this analogy that the engineer is basically synonymous with an operator. Anyway, once you provide the details to the engineer, they can get to work deploying that instance for you. Well, unfortunately, you can't just start speaking to the operator pod running in your cluster. That obviously won't get you very far. Instead, you have to speak a language that the operator pod understands. And that language, as with most things Kubernetes, is primarily YAML. The structure of the YAML is defined by the Kubernetes native resource called a custom resource definition, or CRD for short. It's a resource that allows you to extend the Kubernetes API so that it knows about your custom resources, in this case, the to-do list. Here I have an example of what a CRD might look like for the to-do list operator. So you can see here this manifest file is of kind custom resource definition and uses version 1 of the Kubernetes native API extensions API. It contains important resource-specific details about the to-do list API that we're introducing to the cluster. The name of the CRD, todolists.todos.com, which should be unique and is just the plural name of the resource followed by the group name. The group name is a way to effectively namespace the API so that you don't get conflicts with REST endpoint URLs when extending your API. There's also the version name, which just indicates the version of the to-do list API that we're installing with this file. For the particular version of the API, we specify the schema or valid fields for making API requests to this new endpoint. This way, we can be sure that the operator will get the required information that it needs to operate the resource. For this schema, I've specified list name, max to-dos, and replicas as fields that should be provided when creating or modifying this to-do list resource. Next up is whether the custom resource should be scoped cluster-wide or to a namespace. Here I've said namespaced. At the bottom is a section on naming, where variants of the custom resource's name can be specified, in plural and singular form, as well as defining the kind of resource, similar to how we've specified the kind of this manifest to be a custom resource definition. And then finally, any short names that you want to allocate to the resource for when you're using the CLI. Now don't worry if this isn't making sense immediately. I'll be applying and using this resource, which will help with the understanding. So let's apply this CRD to the cluster and see what happens. I have a copy of the CRD here. First, let's take a look at what happens when I try and get the cluster's to-do lists resource, which is the plural name that we specified in the CRD. No big surprises here. The cluster doesn't know about the resource type yet, so let's apply the CRD. And then again, we can query the resource. Okay, so this looks better. We can see that the cluster now knows about the to-do list's custom resource type. We just haven't created any instances of that resource yet. We can see that the CRD now exists by checking on the command line too. And if you're running OpenShift, you can actually see it in the dashboard as well. You can select administration and then custom resource definitions, and we can search for to do. And here it is here. So like I said before, what the creation of this CRD has really done is make the cluster aware of this to-do list's custom resource and create some new endpoints in the API to interact with it. We can actually see more specific details of that API change. So first, let's check the cluster's API resources. We can see that there's now a to-do lists API resource in there. Secondly, we can actually go a step further and take a quick look at the API endpoints that were created when we applied the CRD by looking at the open API spec that is used by the Kube API server. I'll just start a proxy into the cluster to handle authentication first. Then I'll download the open API spec. And then we can use Swagger UI to view that spec. So it's up to you how you want to do that, but if I'm just browsing, I'll use the Swagger UI Docker container because it's easy. So just make sure that you have Docker running and you can grab this. I'll include a link to this page in the description below. So here we can easily browse the cluster's API. I'll do a search for to do. And here we can see the REST API that's been created by the custom resource definition for the new to-do list custom resource. You can see that this is all namespaced. So for most of the endpoints, you'll need to specify the namespace of the custom resource you're referencing. Depending on whether the CRD is cluster or namespace scoped, you'll get different API endpoints to interact with and manage your to-do lists. All right, so now we can see that our cluster knows about the to-do list custom resource and has API endpoints for us to talk to. The next logical step would be to talk to those endpoints and create a to-do list. This is analogous to the part where we submit the form with the details of the instance that we want to the engineer in our ops room and ask them to create the to-do list for us. To do that easily, we can use probably the most common method of interacting with the API server, applying a YAML manifest. Here you can see what's called a custom resource. It references and follows the schema defined by the custom resource definition. In this case, the custom resource, or CR for short, is of type to-do list, which the cluster now knows about. And the API version specified matches the CRD's group name and version name, so we now know what schema that we're abiding by. The spec field contains the values for the fields defined in the schema section of the CRD: list name, max to-dos, and replicas. So let's go ahead and apply this manifest and see what we get. If you're running OpenShift, another way you could submit this is through the dashboard. So you can come back to the administration custom resource definition page. You can search for your custom resource definition, which in this case is the to-do lists. And then at the top right here, you can click actions and you can select view instances, and then you can actually create a to-do list. That will bring up the YAML form. In spec, you can actually have a look and you can enter these details in here. So we could enter a list name and the max to-dos and so on. You also have the capability to view the spec on the right-hand side of the page and see the data type. Anyway, I'll stick to the CLI so this all stays relevant, not only for people using OpenShift, but Kubernetes as well. So I've got a copy of that custom resource here. So I'll apply that. And now let's query for the to-do lists resource again. Now we can see that the API knows and has the details about our instance of the to-do list stored in etcd. So what happens next? Well, let's take a quick look at some Kubernetes basics to see how the custom resource definition, and the operator all interact. Here I'm just showing a sample cut down cluster with the control plane at the top and the data plane below it. We can see 3 of the core Kubernetes control plane components. The others are left out of the diagram because they aren't relevant for this explanation. So we have the Kube API server. It's connected to the etcd data store, and also we have the Kube controller manager. For those of you who don't already know, the Kube controller manager is a process that runs the cluster's core controllers. So these controllers look after many of the native resources in Kubernetes, like pods, stateful sets, secrets, services, deployments, all those sorts of things. The Kube controller manager includes controllers like the node controller, replication controller, endpoints controller, and others, all of which to service those core native resources. The colored circles are there just to represent that this process houses multiple controllers. So when the cluster starts, these controllers start a watch on the Kube API server for all resources that they have an interest in. So for example, the green circle could be the replication controller, and that will be watching the API server for any new replica set objects that are applied to the cluster so that it can use that information to create pods of the replica set. So when we create a new resource, for example, a deployment of Nginx pods, like you can see here, the cluster's API by default already knows about the deployment resource type. The API endpoints exist by default, and so the API call is successful and the resource is added to the etcd data store. This event then notifies the relevant controllers that have a watch on that resource type, and they begin their reconciliation process. To fulfill reconciliation, the triggered controllers, each focused on bringing their respective resource in line with the desired state, will first get a copy of the desired state, which is the YAML we applied, and also a copy of the current state, which for this cluster begins bare. The controllers will analyze the difference between the two, and they have the smarts built in to act appropriately to move the current state to the desired. The controllers operate in a control loop, so this process of observing relevant events, analyzing, and then acting continues indefinitely, taking one step at a time, reassessing the current state compared to the desired, and acting until they reach their desired state. So this is all just standard Kubernetes. But where do operators fit into this? Well, the operator pattern is actually extremely similar. First of all, the operator is installed as a deployment and can be considered an extension to the control plane. The operator, just like any other controller, takes a watch out on the Kube API server and watches specifically for the custom resource or resources that it cares about. In this example, that's the to-do list resource. Because we installed the custom resource definition, the cluster knows about the to-do list resource and accepts the resource, storing it in the etcd data store. Any controllers with a watch on the to-do list resource are then notified. In this case, that's the to-do list operator. The operator retrieves a copy of the desired state, which again is defined by the custom resource YAML, and then the current state of the cluster, and as expected, has the smarts built in to go about bringing the current state in line with the desired. The operator creates the necessary resources like deployments, services, config maps, secrets, and so on, and potentially other custom resources too. So with that explanation, I think it's safe to say we can just think of an operator as an advanced domain-specific controller. And remember, I'm just showing the creation of a particular resource here because it's easier to reason about. But the operator can be alerted on all sorts of different events, even from other custom resources in the cluster, and take necessary actions as a result. For example, scaling to meet demand or upgrading certain components. An operator can monitor the status of the custom resources that it cares about around the clock, and it can be programmed to make decisions on the fly as resource state changes over time. This makes the capabilities of operators almost endless, and full day 2 operational support is only limited by the logic that you can code into your operator's reconciliation function. Ideally, the goal of an operator is to reach phase 5 of the operator maturity model, so that you can basically have an app run as though it was a SaaS. You don't need to know or care about the inner workings and operations. It just takes care of itself on your cluster. The to-do list example I just showed was really just an example of the most basic operator implementation, which, as you can see here, is at phase 1, which is basic install. There are Helm hooks, the operator SDK, which is one of the tools that you can use to create an operator, provide to you to easily convert your existing Helm charts to operators and achieve that phase 1. Alternatively, if you want to exceed phase 1, you'll need to use the Ansible or Go operator project type when you kick off your operator project. So with the exception of some more behind the scenes resources you'd need for your operator to allow it to effectively manage your custom resources like service accounts, role bindings, roles, and so on, we've pretty much covered the components of an operator. It's worth also mentioning that throughout the example, I was using just one custom resource and one deployment for the operator pod. Depending on the operator, it's common for a single operator install to actually install multiple custom resource definitions and operator pods watching those CRDs. Now, in my opinion, that's all pretty easy and straightforward to understand. But you're probably thinking, why hasn't he actually shown an operator being installed? And maybe you've even noticed there's a few other things that are seemingly important that I haven't yet addressed. And this is all related to one of my opening statements about the tooling surrounding operators that makes them appear more complex than what they really are. I haven't yet talked about things like how and where you get the operator, the CRDs, and other relevant resources for the installation, how over-the-air updates and upgrades of your operators work, how you can package your operator and make it available for others to use, and also what sort of security there is around operator pods having access to other resources on your cluster. The reason I didn't address those topics in this video is because they're handled by something called the Operator Lifecycle Manager, or OLM for short. And OLM is actually an operator itself. So it's an operator that manages operators. There's a small exception here with regard to OpenShift 4, where the cluster operators are actually managed by a separate operator called the cluster version operator. However, any other non-cluster operator will be managed by OLM. If you're running OpenShift, the Operator Lifecycle Manager is installed and operational by default, and you have access to these operators from within the OpenShift dashboard. You can browse the Operator Hub directly from the OpenShift dashboard by selecting Operators and then Operator Hub. If you're running Kubernetes, you can pretty much do the same thing by heading to operatorhub.io. You'll see that if you click on any of the operators and select Install, the very first step before installing the operator itself is to install the Operator Lifecycle Manager. So you need OLM because that's actually what handles a lot of the installation, packaging, over-the-air updates, and general management of the operators. So like I said before, OLM is an operator itself, so it can often be a little confusing trying to explain operators and understand operators when the thing that provides a significant portion of the advanced functionality of them is an operator itself. Anyway, as you can see here, OLM introduces a bunch of new CRDs to the cluster that, as we know now, are used as the API to interact with the operator, in this case, the OLM operator. So in my next video, I'll be going over these CRDs and explaining what they are and how they work together to get our operators installed, kept up to date, and operational using the Operator Lifecycle Manager. All right, I hope you learned something new. So like I said, my next video will be on the Operator Lifecycle Manager, where I'll fill in a lot of the gaps on installation, distribution, upgrades, and all that sort of stuff. So if you enjoyed this video, please leave a like and consider subscribing so that you can tick the bell and be notified when I release that next video. All right, thanks again and bye for now.